Okay, good afternoon, everyone. I'm Jenny from University of Michigan, Ann Arbor, and our project is about the text 3D generative AI on mobile devices. This project is a collaboration between the University of Michigan, Ann Arbor and the University of California, Riverside. For general text 3D generative AI, it will take in a text prompt as its input, and its output will be a corresponding 3D object. Possible application scenarios for such models can be VR gaming or AI-aided product design. You may notice that these applications are heavily based on the mobile devices. So here comes the problems. Well, since these text-to-3D generative AI are usually extremely large, they're not capable for mobile deployment due to the constraints of mobile devices. For example, mobile devices usually have limited memory and limited computational power. Therefore, our motivation is that we want to deploy this text-to-3D generative AI on mobile devices while ensuring a relatively good user experience. Namely, we want this model to have low latency, low memory usage, as well as a relatively good synthesis quality. In order to achieve all these goals, we need to do some optimization. But before we do the optimization, we need to do some measurement to help us identify the most inefficient components of this textual solution of AI, so that we can focus on these aspects and optimize them in order to optimize the whole model. Before I talk about the measurement, I'd like to briefly introduce the background of text-to-3D generative AI. Text-to-3D generative AI is located in the intersection of several AI research areas. From the computer vision aspects, we need to select a 3D representation for our final output. Current 3D representations can be classified into several categories. Well, the first category is explicit representation. And this kind of representation usually will use discrete locations to represent its 3D model. For example, for point clouds, it will use points to represent its 3D model. This kind of model do not need to do intensive computation during the runtime, so that their latency and memory usage are usually quite low. However, as a trade-off, their synthesis quality will also be quite low, because the resolution is greatly depends on the number of discrete locations that they stored. For implicit representation, such as NeRF and SDF, they need to do intensive computation during the runtime in order to render a view for the user. As a result, their latency and memory usage will be quite high. Take the NeRF as an example. The basis of NeRF is a neural network. This neural network will take in the position and the direction that the user is viewing. And then the output of this neural network will be the corresponding predicted color and the density for the viewing direction. As a trade-off, this kind of model will have relatively high synthesis quality due to the computation. So you can clearly see that there's a trade-off between the explicit representations and the implicit representations. And we need to carefully select the 3D representations that can suit our needs when we are going to design our own text-to-3D generative AI for mobile systems. For the generative AI parts, well, the diffusion model is the most widely used generative model for text-to-3D generative AI. It basically involves two processes: the forward diffusion process and the reverse diffusion process. In the forward process, we'll gradually add noises to our training data. And in the reverse process, we'll train a neural network to help us predict the noise that we previously added to the training data, so that we'll be able to gradually remove the noises and recover the original training data. When we are going to generate a new model, we just need to input our text prompt towards the neural network, and we also need to input a purely random representation. It can be 3D representation or 2D representation as shown on the slides, which is a figure. And then the neural network will predict the noise, and we can gradually remove the noise to get our final output. In this project, we measured 3 state-of-the-art text-to-3D generative AI, Pointy, Shapey, and Clip Mesh. For Pointy and Shapey, both of them are diffusion-based models. And the key difference between them is the representation they use. Pointy uses point clouds as its representation, which is explicit representation, while the Shapey uses Latin vectors, which is an implicit representation. These Latin vectors can be used as parameters for NERF or STF, so that SHAPE can run a NERF or STF decoder to render a 2D view for the user. Another difference between them is the number of diffusion processes. Pointy has two diffusion processes. The first process is the base diffusion process, and the second process is the upsampling process. In the base diffusion process, Pointy will generate a point cloud with low resolution. And in the upsampling process, Pointy will upsample this point cloud, and the final output will have a satisfying quality. For SHAPE, it only has one diffusion process, and this diffusion process will directly act on the Latin vectors. And the input noisy Latin vector will be denoised and used as the parameters for NERF and STF. Based on the background information, we can now talk about the measurements. So throughout the measurement, the problem that we want to solve is that what are the bottlenecks of deploying Texel 3D generative AI on mobile devices? So what to measure? Recall our optimization goals. It is clear that the latency, memory usage, and synthesis qualities are the aspects that we want to measure. So here are some basic setup for measurement. We use both server GPU and mobile GPU for measurement. And we also use core dataset, which is a widely used computer vision dataset for measurement. And here are some model configurations. We test models with different parameter counts and also different condition options. For example, there are text-only version, which means that the model will directly transform text into a 3D model. And for image conditional option, the model will first transform text to a 2D image and then transform the 2D image into a 3D model. This figure shows the measurement result of latency and quality trade-off. And the points or the models that are closer to the top left will be preferred when we are going to deploy it on mobile devices. So from the figure, you can clearly see that the image conditional will outweigh text-only models in terms of the synthesis quality. However, text-only models will have slightly better latency performance. The possible reason of it is that the text-to-2D models are usually extremely powerful because there are a lot of training data that are available for text-to-2D models. While for text-to-3D models, the training data of 3D models are quite limited. These two figures shows the breakdown of the latency. And you can see that the diffusion process, which is circled by the red lines in the figure, this kind of diffusion process will cause extremely long latency. And for the glide model here, glide model is a text-to-2D model, and this one is optional, so we'll not focus on this part. And you can replace glide model with other text-to-2D models. For the memory measurement, you can see that the implicit representation can save memory usage during the generation. For Pointy, it is quite obvious that the upsampling process will have much greater memory usage than the base diffusion process. The possible reason of it is that Pointy uses the point cloud as its representation. And if you want to increase the precision and the resolution of your final representation, then you need to increase the number of points in your point cloud. As a result, in the upsampling process, you need to store more points inside your computing memory so that it will lead to a significant increase in your memory usage. However, for SHAPE, as it uses the Latin vectors as its representation, the memory usage of this diffusion process is quite low. Based on this measurement result, it is quite clear that the diffusion process will be our focus of optimization. Currently, there are several ways that can be used to optimize the diffusion process. And in our research, we use distillation as well as the quantization to optimize our diffusion process. The key reason of this is that both of these optimizations can be easily generalized for other diffusion-based models. Well, for some optimization methods like neural architecture search, this kind of optimization methods are usually quite device-specific, so that you cannot easily generalize them. For distillation, the key idea of it is to speed up the model by eliminating the steps. We'll have a student model, which is a smaller model with less steps, and the original model will be the teacher model with more steps. And the student will try to mimic the behavior of the teacher model during the training so that it will have similar performance as the teacher model. And we can do the distillation for multiple times, and our student will become the new teacher. This figure shows the final results of the distillation. And you can see that the synthesis quality will severely degrade at lower latency. For quantization, the key idea of quantization is to speed up the model and reduce the memory usage using the parameters with lower precision. For example, initially you may use 32 bits to store the parameters inside your machine learning model, but after the quantization, you may sacrifice the precision and just use 8-bit to store all these parameters inside your machine learning model. As you can see in this table, the improvements of quantization is quite limited, and the degradation in terms of the quality is quite obvious. So some further efforts may be needed. For example, there are some current research that are focusing on parameter by parameter quantization. So even in the same layer, for example, the linear layer here, you may have different precisions for different parameters. Some of the parameters in this layer might be 32 bits, while others may only be 8 bits. So briefly summarize what we have talked about so far. So multi-objective and customized optimization might be needed for the mobile deployment of text-to-3D generative AI. And another conclusion is that Shapey actually outperforms Pointy when it comes to the mobile deployments, possibly due to the implicit representation it uses. And in terms of the synthesis quality, the image-based or image conditional options will outperform the text conditional option. Yeah, that's all I have today. And any questions?